Welcome to Maths with EJD. Broadly, we're talking about numerical optimization techniques, and we've come all the way down to where we talk about non-linear programming, okay? Non-linear programming. And as far as non-linear programming goes, we've seen different methods for dealing with it, like the penalty method. We also saw the barrier method. Then we looked at the generalization of Lagrange multiplier, which leads to the Karush Karush Kontoka or KKT conditions. Okay. And lastly, we are currently considering evolutionary algorithms. Evolutionary algorithms. So these are different algorithms that borrow leaf from um, you know, from biology, metallurgy, and all of that. So on here we have seen first of all simulated annealing, which copies cooling in metallurgy. Then we saw taboo search, which makes a list of possible solutions and eliminates them as better solutions are obtained. Because of that memory, we don't revisit eliminated possible solutions. And after that, we've seen the genetic algorithm. Of course, we've seen genetic algorithm under the derivative-free methods for numerical optimization techniques. And after genetic algorithm, we saw particle swarm optimization. Particle sum optimization takes a cue from how birds flock together and how fish school together or as they swim. Okay. Um, so in this video, our focus shifts to uh the last I'm going to take for evolutionary algorithms, which is differential evolution. Differential evolution. So, of course, just like I said, we've taken care of penalty method, barrier method, Karush-Kontoka conditions. We've done simulated annealing, taboo search, genetic algorithm, particle sum optimization. Now the focus is on differential evolution. So, differential evolution. Okay. So, I mean, for a lot of people, that this might just be a new concept. So differential evolution. After now, I just refer to it as DE, is a population-based optimization, is a population-based optimization algorithm used to solve complex optimization problems, especially in nonlinear programming. Okay. It is particularly effective in situations where the problem's objective function, where the problem's objective function is non-differentiable, non-differentiable, multimodal. That is, you have multiple minimum or maximum, multimodal, or contains noisy data. Noisy data. So this is giving me the feel of some kind of machine learning inclination. So differential evolution works by iteratively, iteratively improving candidates, by iteratively improving candidate solutions through a combination, through a combination of mutation, crossover, and selection. And of course, this looks like genetic algorithm a lot, except that the approach may be slightly different. Generally speaking, all the evolutionary algorithms, they seem to have the same kind of pattern. Okay, with this in the bag, can we go ahead and see some key things? First of all, let's talk about key steps in differential evolution. What are the key steps here? As usual, we have the initialization. So you have that initial guess or whatever in every situation, initialization. So you have a population of candidate solutions initialized randomly, and each solution represents a vector in the solution space. Okay. So here you have population size, you have population size n, and you have the dimension d, dimension d. I mean, this is simply talking about number of variables, number of variables. So if it is 1D, you're talking about one variable. If it is 2D, you're talking about two variables, like x1, x2. One variable will be like x1. Two variables, that's like x1, x2, x and y. That's what the dimension is basically about. And then number two, you talk about mutation. You know, it's evolution, right? But it's differential. So differential evolution. So for mutation, we say for each individual solution xi, so for each individual solution xi, a mutant vector. So we have a mutant vector vi, which is generated by adding a scaled difference between two randomly selected individuals from the population. Okay, so here you have vector v sub I equals xr1 plus f into xr2 minus xr3. Okay, so that is the mutant vector vi. So we have this now. Okay, so of course all the xr are talking about the solution. Maybe xr1 is like the first, xr2 second, and all that. Okay, now we have the crossover, which is a standard talk when it comes to evolution. So we have crossover, or what we call recombination in genetic algorithms. So in this case, the mutant vector, the mutant vector vi is mixed with the current solution, the current solution xi to create a trial vector ui, and then crossover is done element wise using a crossover probability CR. Okay. So here we see that UI, that trial vector UI, is a step function vi comma j if random between 0 1 is less than the crossover probability, or j is equal to j random. Okay, j is equal to j random. And then the other one, uh so then the other part is xi comma j otherwise. Okay, otherwise. So that's what UI is, the trial vector. Okay, and that leads us to the next step. That should be that's number 4 now, where we talk about selection. 4, selection. So after generating the trial vector UI, its fitness is evaluated. I mean, this is like common to almost every evolutionary algorithm method. The fitness is evaluated, and then the trial vector, the trial vector replaces the current solution, the current solution xi, if it provides a better objective function value, a better objective function value. Because this is standard for evolutionary algorithms too. So you have f of ui is less than or equal to f of xi. So if this happens, we can do our replacement as required, and we go for step 5 where we talk about termination. So termination, like that. So termination. So here the algorithm terminates. The algorithm terminates when a stopping criterion, when a stopping criterion is met, say number of iterations, right? Such as a predefined number of iterations, or convergence to a solution within a given tolerance. Okay. So with this in place, can we switch over and talk about example? We want to minimize f of x equals x1 minus 2 squared plus x2 minus 3 squared. That's all we have. No constraint, just that unconstrained problem. So here we go for step 1. So for step 1 now, initialization. So here we want to assume a population of size 4. So n is equal to 4. That's population size. And the dimension is 2. Dimension is 2 because we have x1 and x2, basically. So we have variable x1 and variable x2. Those are the things that determine the dimension. So then with that, we can have a random initial population. Random initial population. Random initial population. So say x1 is 1.5, 2.0. Then x2 is 2.5, 3.0. Then x3 is 0.5, 1.5. And then x4 is 2.0, 3.5. Like that. So randomly we could, but you discover that all these values you are picking they are hovering around 2 and 3. So these 2 and 3 you see here. So they are hovering around all those values. Okay. So with that in place, we go for step 2, where we begin to talk about mutation. Step 2 is about mutation. So um, for for each individual, for each individual, we generate we generate a mutant vector. For instance, I mean, we've done this for other methods, so I won't just go too far. So for instance, for x1, x1 is 1.5, 2.0. So for x1, right, we have v1 to be equal to, we have v1 to be equal to x2 plus f into x3 minus x4. Okay. So that's the kind of idea we have here. So for V1 now, so V1 is equal to x2. X2 is 2.5, 3.0, right? So we have 2.5, comma 3.0, okay, plus f. Okay, what if we take f to be 0.8, okay? F is 0.8. So that's like a kind of scaling factor. So we take F to be 0.8, 0.8 into x3. So what is x3? X3 is 0.5, 1.5. So that is 0.5, comma 1.5. Okay. Minus x4. X4 is 2.0, 3.5. That's 2.0, 3.5. Okay. So with that in place, let's see what we can have. So that's V1 equals 2.5, 3.0 plus 0.8 into, so if 0.5 minus 2.0, that's like, that's minus 1.5, comma 1.5 minus 3.5, that is minus 2.0. Okay, minus 2.0. So then we have V1 to be equal to 2.5, comma 3.0 plus, now 0.8 times 1.5, right? So that's 122 decimal places. That's minus 1.2. So this is minus 1.2. When you multiply 1.5 times 0.8. And 0.8 times 2.0, that's minus 1.6, right? 0.8 times 2.0, that's minus 1.8. So now we have V1 to be equal to 2.5, minus 1.2. That is 1.3, comma 3.0 minus 1.6. That's 1.3, 1.4. So we have our V right there. So do we remember what V used to be? V is the uh is the scaled difference. It is the scaled difference. Okay. So we have that. So V1, V2, V3, V4. So it means that if we need V2, right, then we can go to 3, 4, 1 back. So if we are going to do V2, so this would be like X2, I mean V2, X3, X4, back to X1. I think that's what that should be like. And then we have a scaling factor, or the crossover probability. So, uh, no, F here is 0.8. So we can pick that value between 0 and 1. Like we said before, I think we talked about this somewhere already. So it's some kind of scaling value. Now we have done the mutation thing. So we have the mutant vector V1 now. So you can see it produced a whole new result on its own. So that's a mutant. And then we go for the next step. That's step 3. So we have step 3 where we talk about crossover or recombination maybe. So assume a crossover probability. Assume a crossover probability that is CR equals 0.9. So crossover applied element-wise will now be you have U1. This is a trial vector now. U1 equals 1.3, 2.0 from where we are coming from. So 1.3, 2.0. So this is with x1 equals 1.5 and v1 equals 1.3. So replaced, but now x2 is 2.0 remains unchanged. Okay. So, we're talking about x1 before was 1.5 and 2.0. But what has happened here is that, so the 1.0 now, so with x1 equals 1.5 and v1 is 1.3. So replace, but x2 remains 2.0. Okay, that's for x1, x2 like this. So, that's crossover happening right there. So U1 is 1.3, 2.0. So if I guess we have to check this rule that was stated already. So Vij if random. So this is the rule that is working in that place. And that's how so if we apply that rule properly, then we arrive at this particular U1 now. So with this U1 in place, then we can talk about the next step, which is selection. Step 4, that is selection. So we evaluate the objective function for x1 and u1 such that we now have f of x1 equals 1.5 minus 2 squared. So plus 2.0 minus 3 squared. All right. Because our x1 is talking about 1.5 and 2.0. If you remember, yeah, 1.5 and 2.0. So with this now we have 1.5 minus this minus 2 is minus 0.5 squared. 2.0 minus 3 is 1.0 all squared. So we have 0.25 plus 1.00, and we have f of x1 to be equal to 1.25 like that. And then we can also have f of u1. F of u1 is 1.3 1.3 minus 2 2.0 squared, all right, plus 2.0 minus 3 squared. Of course, U1 is what we have got from the crossover. So this is U1 now. That U1 is what we are using there from the crossover. Okay, so from this now we have minus 0.7 squared plus minus 1.0 minus 1.0 squared. So this is 0.49 plus 1.00. So now we have 1.49. That is f of u1 is 1.49. Okay. So in this case, since f of u1 is greater than f of x1, as you can see, f of u1 is 1.49, f of x1 is 1.25. Since f of u1 is greater than f of x1, okay, it means we keep x1 because the problem is a minimization problem, if you remember. So if it was maximization problem, we have to displace it. So we are minimizing, so we keep the smaller value. So we keep x1 and we continue the whole idea with that. So we keep x1 and then in step 6, step 5 now, we repeat process. So step 5, repeat. So the same process is repeated for all individuals in the population. We only did X1 now, so we have to go to X2, X3, and all that. For individuals in the population until the termination criterion is satisfied, maybe number of iteration or some value of the objective function. All right, knowing that this can be pretty tedious, Python always comes to the rescue. So look at this now. We have so differential evolution for nonlinear programming. And so here we're using Matplotlib, and we have some 3D visualization since we're working with X1, X2, and want to see a three-dimensional kind of picture. So the function is defined in line 8, as you can see. So x1 minus 2 squared plus x2 minus 3 squared. Of course, for Python, counting start from 0. That's why we have x of 0 minus 2 squared, like that. Then we initialize the population randomly within bounds. Okay, that's what's happening around here. So for the differential evolution, we have the function already defined, or that we defined, right? We have the bounds, which has been defined also. Population size, we are taking 20 here. So, in what we did manually the other time, we took 4. But I mean, evaluating 4 alone is a lot of trouble. But with coding, we can easily do a larger population size. And we want maximum iterations to be 1,000. So imagine having to do 1,000 iterations manually. Then F here is 0.8. That F you saw at the other side. And then CR is 0.9, which is the crossover probability. And the tolerance is 0.000001, right? So that's the tolerance. That's like a stopping criteria right there. And then we also want to visualize this whole thing, so you can study the code better. You can get it on Facebook, copy it to your own IDE, right? And run it, maybe Jupyter Notebook or VS Code or any platform interface you use, like that. So with this in place now, we can visualize to see what's happening. We have our results bound between -5 and minus 5 and 5 for each of the parameters. So from what I've run now, you see that we have x1 comma x2 to be equal to 2.8163 comma 2.7782, like this. And then we now have the best fitness, the minimum value now. So you see, you can see all the values all over the place. And finally, we get the best results somewhere very down. and that is f of x1, x2 minimum is 0.7154. Of course, this is the result I'm taking. If I run it again, because of randomness in it, I'm going to get another set of results altogether. Okay, so you can see the result has changed. But of course, if we want something really important, we can do seeding to ensure that the result is always the same. Okay, but I mean, this is the code generally to make us see what's really going on right here. Okay, so Python to the rescue. We took population size of 4 here normally, but in that case, the situation is different. So we can report that. So from the Python code, with population size being, I think it was 20. The dimension, of course, remains to x1 and x2. Then we also had f to be, I think, 0.8, and then the crossover probability was 0.9. So with that, okay, we have, of course, the other criteria I should have mentioned, but you can see it in the code. So we have x1. Actually, it should be x1 star, x2 star. That's like optimal solution, which is 2.8163, then 2.7782. So if you change the parameters, you get different sets of solutions. And objective function value minimized at f of x1 star, x2 star, or just f of x star, and that is 0.7154. So that's what I've chosen to pick out of that. So if you take the code, you may not get exactly this, because each time you run it, you get a different set of results. But we can actually make the result fixed. So with this now, we see differential evolution. So in conclusion, right, we see that, okay, let's talk about some kind of conclusion. Okay. So we see that DE is simple yet powerful. Simple yet powerful. Okay. Optimization technique for solving nonlinear problems. It is especially useful for problems where the objective function is complex and traditional gradient methods might fail. So, like we know, it handles continuous. It handles continuous non-differentiable and high dimensional optimization problems effectively. Okay, so let's take a practice, as we call the whole nonlinear programming thing a wrap. In fact, numerical optimization techniques, it's a wrap. There are many other methods we can talk about, but if anything comes up in the future, I can revisit this. But I think I've covered a significant portion of this. So the practice, given the following nonlinear, following the following nonlinear, okay, I was gonna hurry up. Given the following non-linear optimization problem, which is to minimize f of x equals x1 minus 3 squared plus x2 plus 1 squared. Okay. So step 1, right? Like we always do, step 1, initialize a population of 4 individuals, just like we did before, with D equals to, of course, we have X on and X2, so just two variables clearly. That's step one. Step two, apply mutation. Apply mutation, crossover, and selection steps, using a scaling factor. So F is a scaling factor. F equals 0.9 and a crossover probability CR equals 0.8. Okay. Then step three. So in step three, perform optimization. Perform optimization for 5 iterations and determine the final solution. All right, so let me see your solution or your attempts at least in the comment section, either on Facebook or on YouTube. Okay. You can get the code only on Facebook, sadly, but that's okay. You can just do that, copy it out and play with it, tweak some parameters and see how things behave. That's how you can learn. And then, of course, in the comments, let me know how helpful these videos are for you. Let me also know if there's a problem you like me to solve or a topic you like me to treat. And then, of course, if you have not subscribed, please go ahead and subscribe. That'll be highly appreciated. So for those who have subscribed, thank you so much. And if you have subscribed or you're just subscribing right now, don't forget to um don't forget to hit the notification bell so you can always get alerted each time a new video is released. So after this topic, I'm going to talk about differential equations, which I know a lot of people have been waiting for. I don't want to miss any of that. So I'll take, just like my approach has been, every topic I take it from the very basic. What is the topic? What is it? Like the definition, and from there we scale it to at a very advanced level. So I'm going to start differential equations from simple bits like what is differential equation, what are the types of differential equation, and things like that. So you don't want to miss any of that. So please be sure to subscribe and hit the notification bell so you don't miss out on any of this. And of course, like and share so that more people can have access to this content, which has been very helpful to a lot of people across the world. Till I come your way again, keep doing maths right. Bye.